Hello and welcome to free online video lessons presented by learninguniverse.com, that is learning-universe.com. This is the part 1 of the 4-part video of the lesson Atomic Structure. In part 1, we look at the various models of atom, starting with the Dalton's atomic model, going through J.J. Thomson's atomic model, and culminating with Rutherford's model of the atom. We begin with the Dalton's atomic model. Dalton's atomic model is one of the fundamentals of physics and chemistry. This theory of atomic composition was hypothesized and partially confirmed by the English chemist and physicist John Dalton in 1803. Dalton came with his atomic theory as a result of his research into gases. He discovered that certain gases only could be combined in certain proportions even if two different compounds shared the same common element or group of elements. Through deductive reasoning and experimentation, he made an interesting discovery. His findings led him to hypothesize that elements combine at the atomic level in fixed ratios. This ratio would naturally differ in compounds due to the unique atomic weights of the elements being combined. This was a revolutionary idea, but further experimentation by himself and others confirmed his theory. The findings became the basis of Dalton's atomic laws or model. These laws focus on 5 basic theorems. First, pure elements consist of particles called atoms. Second, atoms of an element are all the same for that element. That means gold is gold and oxygen is oxygen down to the last atom. Third, atoms of different elements can be told apart by their atomic weights. Fourth, atoms of elements unite to form chemical compounds. Finally, atoms can neither be created nor destroyed. Their grouping only changes. The last law of Dalton's atomic model was at the time considered true for all reactions. This was later corrected with the discovery of nuclear fission and fusion. So we now know that this only holds true for chemical reactions. Like other scientific theories, Dalton's atomic model has been perfected over time with the research and discoveries of other scientists. We now know that the atom can be divided into even smaller particles, and we have even discovered the actual internal atom structure, even able to view it through modern technology. Next, we move on to J.J. Thomson's atomic model. The plum pudding model of the atom by J.J. Thomson, who discovered the electron in 1897, was proposed in 1904 in order to add the electron to the atomic model. In this model, the atom is composed of electrons, though Thomson still called them corpuscles, surrounded by a soup of positive charge to balance the electrons' negative charges, like negatively charged plums or raisins surrounded by positively charged pudding. The electrons, as we know them today, were thought to be positioned throughout the atom, but there were many structures possible for positioning multiple electrons, particularly the rotating electrons in rings, which we will talk about later. Instead of a soup, sometimes the atom was also said to have a cloud of positive charge. Thomson's model was compared, though not by Thomson himself, to a British dessert called plum pudding, hence the name. Thomson's paper was published in the March 1904 edition of the Philosophical Magazine, the leading British science journal of the day. In Thomson's view, the atoms of the elements consist of a number of negatively electrified corpuscles enclosed in a sphere of uniform positive electrification. The last model in this video that we will focus on is Rutherford's atomic model. In 1909, Ernest Rutherford, a former student of J.J. Thomson, directed the now famous Geiger-Madsen experiment. Initially, he chose Hans Geiger to assist him in bombarding a thin metal sheet with high-energy alpha particles that were being emitted by a radioactive source. They chose gold as the metal since gold is highly malleable and ductile. The next problem was to devise a screen that would fluoresce when alpha particles hit it. Geiger and Rutherford devised a screen that was coated with zinc sulfide. It produced sparks called scintillations when alpha particles struck its surface. Often, Geiger would be left in a darkened room to count the scintillations, which was an essential part of the experiment. In the experiment, Rutherford directed Geiger to find the deflection angle of the alpha particles after passing through the gold foil. On Geiger's request, Ernest Madston, another student of Rutherford, was roped in to exactly observe the range of deflection angle and the number of such deflections. Marston noted that the majority of alpha particles passed without deflection, while some showed small deflections. However, there was 1 in 20,000 alpha particles which suffered a deflection of more than 90 degrees. 2 years later, in 1911, Rutherford presented his analysis of the observations, leading to what is known as the Rutherford's atomic model. Now let's understand the Geiger-Madston experiment. A gold leaf that was 5 into 10 to the power minus 7 meters thick was taken. It was then surrounded by a circular screen that had been coated with a paint of zinc sulfide. A vessel coated with thick lead contained radioactive polonium-214, an alpha particle emitter. This is the path of the alpha particles. Rutherford expected that almost all the alpha particles should pass through without deflection if Thomson's model was correct. This was because in Thomson's model, the positive charge was dispersed throughout the atom. Therefore, the electric field necessary to deflect the alpha particles was not available. But the actual observation was more astounding. Most of the alpha particles passed straight through as expected. There were some which showed minor deflections. Then there were some that showed major deflections. Including a rare phenomena where an alpha particle got reflected in the direction from which it had come. Based on these observations, Rutherford concluded, since more than 90% of the alpha particles went straight through the gold foil, it suggested that most of the atom is empty space. Since alpha particles were traveling with the speed of approximately 1 into 10 to the power 7 meters per second, they carried a great amount of momentum. Such a particle could only be deflected if it is assumed that all the positive charge of the atom is concentrated in a very small volume inside the atom. This was called the central charge region. Later, this was named the nucleus. In fact, Rutherford was so stunned by the result that he once remarked, "It was quite the most incredible event that has ever happened to me in my life. It was almost as incredible as you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. On consideration, I realized that this scattering backward must be the result of a single collision, and when I made calculations, I saw that it was impossible to get anything of that order of magnitude unless you took a system in which the greater part of the mass of the atom was concentrated in a minute central core. It was then that I had the idea of an atom with a minute massive center carrying charge." Rutherford calculated the approximate diameter of the nucleus to be 1 over 4,000 times that of the gold atom. Now it is believed to be 1 over 20,000 times that of an atom. Since the high-speed alpha particles are not able to dislodge the nucleus of the atom, it implied that almost the entire mass of the atom was located in the nucleus itself. Though neutrons had not been discovered yet, Rutherford did predict the existence of neutral particles with mass. He discovered the protons in 1920. Rutherford did not make the connection between the central charge and the atomic number. A month after his paper was published, the proposal regarding the exact identity of atomic number and nuclear charge was made by Antonio van den Broek and later confirmed experimentally within 2 years by Henry Moseley. Here we look at how the experimental results work fine with the Rutherford's model of the atom. As we can see, majority of alpha particles pass through the atoms while some suffer small deflections. There are others that suffer large deflections. Including the rare phenomena where a particle bounces back in the same direction. Sometimes you can have multiple deflections for the same alpha particle. It is noteworthy to see that Rutherford's model served to concentrate a great deal of the atom's charge and mass to a very small core, but didn't attribute any structure to the remaining electrons. It did mention the atomic model of Hantaro Nagaoka, in which the electrons are arranged in one or more rings with the specific metaphorical structure of the stable rings of Saturn.